We can wait for some more minute.
So here master's, bachelor, all are there, students. Shantanu?
Yes, ma'am. We have forwarded the mail to everyone. Particularly, this was for EPD students only, but any interested people from other design background can also join. So
Okay. Yeah.
Or did you send it to? I think they are not aware. Shantanu?
yes, sir. I've sent the mail and gentle reminder as well. I have sent on WhatsApp as well. They should be joining in some time.
Okay, we can
Fine.
wait for 2-3 minutes. Actually, yesterday Bora sir told me to present, so I couldn't prepare for a specific topic. So this is an overview, that's why.
You can show your case studies.
Yeah, actually, what I thought of, what I did in my PhD research, I can
Yeah.
give an example that so people
Okay,
can relate.
Yeah, so they will get an idea of the systematic process.
Yeah, that's why.
Ma'am, we can start if you want. People will join.
All EPD students are there?
Mm. Yes, ma'am. Mostly.
Mostly. Okay. Okay, they can join.
Anyway, we are recording the session, so they may refer the video. Yeah.
Okay.
Okay, go ahead.
Okay. Okay, so let's start to the topic. So the topic is an overview of the different steps in electronic product design. So can you please tell me what is an electronic product? Anyone from the students? Means what's the difference between an electronic product and product without, means that day you people have shown some products. So what is the basic difference between that?
An electronic product will have some sort of controlled logic and current flowing through it, which is doing some work, and any other traditional product may not have that.
Yes, yes. So the thing is that electronic product has that the capability of measuring the physical parameters and control. Yeah, what you told, that absolutely correct. The decision making parameters, those things are present in the electronic product. So how to design that electronic product? I will show these things. So I will share my screen. Let me share. Okay, is it visible?
Yes, ma'am.
Okay, let me introduce myself first. So I am the assistant professor on contract joined here in the Department of Design, IIT Guwahati. So my background is in electronics and instrumentation. I have done my PhD from IIT Kharagpur, and where my main thesis work was is the development of a product. So that product is a milk tester, which can detect and it is a low cost, of course. So to detect the composition and quality of the milk. So how did I develop that thing? What was the design criteria? So all those things I want to share with you today. So that can give you an overview of the different steps which are required in any electronic product design. So let's start. So already it is done. Now we are coming to the different processes. So if we characterize this, there are different processes, just the identifying the problem, then feasibility and importance. So I will cover each and every point with example. So, and that example is from that, the practical example, the developed instrument. So let's start with the identifying the problem and what is the feasibility and importance of this, to identifying this problem. What is the importance of that problem? So if what I have seen in this is a practical study. So what I have seen that milk is one of the staple food which is consumed all around the world. So if we see the price of this milk, so it is basically based on the composition, that is that fat, solid, not fat, and protein in the milk. And another one is the based on quality. So we generally prefer to have the milk from the branded, means the packaged milk we generally purchase. We don't want to have the loose milk because we prefer that we should have the quality. So that's why we go for this packet milk. But why don't we go for the loose milk? Because we see that there are different adulterants, maybe they can mix with this, and also the quality can be degraded by different kind of parameters like the non-hygienic milk collection, then cleaning and disinfection, then milk preservation. So different adulterants like water, urea, the detergent, sodium hydroxide. So every adulterant has their own means it is used for different purposes. All the adulterants are used for different purposes. So they are used in India. Basically, in India, it is there. So from there the idea came. So it is the identifying the problem. So first step what we have done is identifying the problem. After the identification, the next is that so the first 2 points are done, identifying the problem and what is the feasibility and importance of this, what we are going to develop. So what are the importance? So we found those two things. Now after identifying the problem, we have to go to the literature review of the ongoing research. So for why do we need this literature review? Because if we go and if we see only the product parts, then we can miss something, because sometimes the research first at beginning of any product, some research is going on. So maybe it may happen that there are some research, but it is not is done in the product form. So if you do in another means research, and if it both are similar, then you don't have the novelty of that product. So you have to do both the literature review of the ongoing research as well as the existing products. So for that, we first did the literature review of the research paper. So for that, first I have checked the test for composition. So is there different? What are the different methods used for the composition? Composition means the milk, fat, protein detection. What are the composition of milk and what are the research for that? So we found that there are chemical methods, then light scattering method, ultrasonic. So different methods are there. But what are the drawbacks of that research? So we found the drawback that it needs that sometimes a chemical knowledge, or the instruments what we use for that detection, that are the expensive instruments, and also needs that expert knowledge for operating those instruments. Just like if we for chemical testing, we need the chemical knowledge, otherwise we cannot detect. And if we go for that fluorescence spectroscopy, so we need that spectrometer and all those things. Then again, we found what are the research for test for quality. Quality means whether their adulterants are mixed or not. For that, different methods are there in research papers. So, but again, the problem is that it's basically chemical related and expensive instruments. So after that literature review of the research is done, we will see that whether any instrument is there by using the research, whether any instrument is there in the market. So for that, we'll go through the different the research, means the commercially available, what are the instruments we need to find out. So for that, we found that this is the first one is the Gerber centrifuge that is used for the fat content detection. Then different type of milk tester, lactometer, you are all unknown of these things. Then lactoscope, these are also used in the high industries, large industries. So, but all the in these commercial instruments which are I'm showing here, these are not able to detect the any presence of adulterants in milk. And another thing is that no commercial instrument to test only the adulterants. So it is whatever the instruments are there. First, it has to check the fat content, then the protein content, these things, because these are very much used in the industries. And another thing is that industries do not encourage only the adulteration detectors. So we found that only 3 instruments are there which can test both the adulterants and the composition in milk. So for that, we found one is that Yama, the first one is NIR 350, and then the Milko screen. This is from Denmark, and one we have found that it is from CSIR Seri, India, that laboratory. But later we found that it is in the research only, and what they have claimed is the research only. That instrument is they made, but it is not in product form in the online market. Okay, so basically the 2 main instrument we can say that this is EMIR 350 and the Milko screen. But if we go for the cost or the of this instrument, so we can see that it's cost 4 lakhs, 5 lakhs in Indian money. So from that, actually, the idea came to develop a low cost and easy to handle milk tester, which can determine the composition as well as can detect adulterants with the different fat content milk. So you can see that first we have checked the what are the problems, what are the instruments, what are the research are there. After that, you have to make the decision, okay, these are the problems and what we can show some novelty. So we can see that we have to check, we have to build an instrument which can be affordable by the small industries as well as the household, and especially for the household purpose, because we cannot buy it as a customer. The normal people cannot buy a instrument of 4 lakhs, 5 lakhs for the milk testing purpose. So for this idea came. So this total thing is called this ideation and the research. So you have to do, and the concept also you need to design that what will be here, that is that I have to do the low cost instrument so that it can be affordable by the small industries and the household. So these are the basic part of any product development. So maybe it is an electronic product, maybe mechanical, anything. So you have to go through this ideation and the research process. Okay. And after this, whenever we are talking about the electronic product, then there are some differences. So the electronic product, what we may see everything means in day-to-day life, we have seen different electronic products. And by the way, can anyone differentiate between what are the electronic products and what is the electrical product? Anyone?
Electronics has small voltage control compared to electrical products mostly. Um, Generally, electronic product will have devices like transistors, ICs, which are running on 5 volts, 3.3 volts, and not particularly running higher voltages or currents through it.
Okay, so maybe can we say that the bulb, it is an electronic product or electrical product?
Incandescent bulb is electrical product.
So wherever the current is converted to different form of energy, means maybe the light, heat. So that things but it's almost similar, but you need to know these things to differentiate that what are the electrical products and what are the electronic products. So electronic products, you can amplify the voltage, then you have said that it has a transistor, it has that resistance, capacitance, these things will be there. And mainly the so whenever we are going for this electronic product development, so we must have some capability of measuring the physical parameters. So how do we measure the physical parameters? By use of the sensor. So electronic products should have some sensing capabilities. And why do we need that sensors? Because the sensor will sense that physical parameters like that, the temperature, light intensity, whatever. And then it is converted to the electrical signal. And that electrical signal, what will have, that is means that is transformed to the electrical signal conditioning circuit. And that signal conditioning circuit will give a voltage or any means basically we do for it is a voltage, so that a microcontroller can have the facility, means it will have the decision making capabilities. So all those things we need for an electronic product. So I will explain one by one. So we need that sensor design, and there is a difference between that the electronic product and the mechanical product. So we need the sensor. So how to do? So you can design your own sensor, means it may be customized sensor, or you can have, if you are beginner, so you can have the readily available sensor from the market. As you can see that in your product that display, you people have shown some one cycle was there would have the ultrasonic sensor. So that thing you have purchased from the market. But if you are in research, maybe some of you will go for research. So that is one of the another field of the sensor design, fabrication, then characterization, those things. So how to involve those things in the electronic product design. So first we'll go for sensor design. Let's say we are we are not purchasing any commercial sensor, because here my main aim was to develop a low cost instrument. So how to make a low cost instrument? To make a low cost instrument, you need to have a low cost sensor. So whatever we have seen, the ultrasonic method or chemical is a low cost, but no means you need the chemical knowledge. But our aim was to make an instrument which can be means no technical knowledge is required to operate that instrument, as well as it should be a low cost. So for that we are going for this low cost sensor fabrication. So I just for your knowledge, I am just giving an overview of what the sensor I used. So this is many of you have seen the PCB board. So the what are the basic material of the PCB board? A rigid PCB. Anyone? So the basic material of any PCB is the FR4. It is mainly used, means 80-90% time it is used for FR4. This is the fire resistant board, and it is a particular FR4. And these actually have copper cladded in both sides. It is having the copper, and it is very cheap. And this copper cladded epoxy means this the board we took and we cut it into the dimension, and after that we made it a coating of a particular chemical, that is a polymethyl methacrylate. Why did we do this coating? Because we found that after the coating there are some porous nature on the top of the, I can take pointer. So this is the porous nature, we found it. And because of this porous nature, when we are dipping the sensor inside the milk, then because of different adulterants and the ionic concentration of the milk changes, and ions are diffused through this porous coating. And because of this, I think you know the phase angle of, because it is working as a RC circuit, means the resistance and the capacitance is in parallel, and because of that the phase angle of that RC circuit got changed. So whenever we know that phase angle is tan inverse reactance by resistance, so whenever the adulterants quantity is more or different adulterant is there, ionic concentration are more, and because of that conductivity is increased, and resistance is inversely proportional to the conductivity, so that the phase angle was changing. So no need to go in the details of, I just want to share this thing because my main aim is that this is a simple low cost sensor, because if you see the cost, it is around one cost sensor cost 12 INM. And for this actually, so it can detect different adulterants. So but the one problem what we faced is that the sensor, the diffusion process is a random process. So sometimes the phase angle, it is not giving the exact similar phase angle in the multiple dipping. So there are some differences, and how to make an instrument with this sensor, it was a challenge or it was a problem statement for that. So to how to make the instrument with this sensor, and of course if we can make a instrument with this sensor, it will be a low cost instrument. So for that actually you need to do some sensor characterization. And I can say that if you go for any readily available sensor also, you can find some data sheet. And that data sheet is actually the sensor characterization they have done. But whenever you are purchasing, you should follow that data sheet. Maybe when you are purchasing some ICs and all those things, so you will find that data sheet. And that is actually the characterization of that particular IC or characterization or parameters of that sensor. So, but here I have that my custom sensor. So for that, I need to characterize my own. So what are the different parameters? For different parameters, you need to do some extensive experiments, because you need a larger data set for the data analysis. So here all those things come: sensor design, then sensor characterization, data analysis, all those things are working together to make the instruments giving the better, means accurate or precise results. So some of the parameters I will show today how to do this. So first, if we can see that the operating and detecting frequency, because this sensor has because we are telling that phase angle is changing. So that means it is a RC sensor. So what we are giving a voltage and the frequency to the sensor. Means we are passing a sine wave to the sensor. Okay. So, but at what frequency it will give you the better result or the maximum result. So for that, what you have to do, yeah. Okay. So for this operating and detecting frequency, first let's say for this. So if we go for this, we have seen, we have given a frequency sweep. Okay, so it is 0 to then 10,000 hertz or 1 megahertz like this. So for that, we have seen at what frequency it is giving the maximum result. The difference is maximum, because if we see the difference is maximum, then only we can detect. So here I am not going the details. So we found one of the frequencies 5.6 kilohertz. For actually we were also experimenting different fat percent milk. So for that also we found. But here for simplicity, you can see that two frequencies we found. One is 5.6 kilohertz and another one is 500 hertz. So we took these two frequency for our operating and detecting frequency. Okay. And then we saw that what is the dipping time, because earlier we said that it is a diffusion process. So for diffusion process, you need to wait for some time to get settled down. So for this, what are the settling time when we are repeatedly dipping, and what are the settling time when we are using for first time, or when we are using for after 2-3 hours. So you need to do all those experiments rapidly, so that you will find a solution, or you will have that one parameter that, yeah, these are the dipping time. So we found that this is a 6-minute dipping time, then 1-minute dipping time for when it is a continuous use. Then we found that, okay, we are dipping the sensor, but whether the environmental temperature, means the room temperature, whether we need to do it in cold temperature, hot temperature, what are the possibilities. So we found that means we have gradually increased the temperature. Why? So for that we saw that at the temperature of 42 degrees, so if we measuring 5 repetition, 10 repetition, and we are getting some data. Data means that is a phase angle data we are getting. So this phase angle, we are seeing that spread is minimum at 42 degrees centigrade temperature. So whenever the spread is minimum, that data is correct. So we have to interpret all the, and we have to analyze those data with the help of different statistical analysis. So here I have used one, this is called the box plot analysis. So in that box plot analysis, it will give you the maximum, minimum, and then what is the spread, standard deviation, those things, and we found that it is the minimum. So we have to take this temperature as the optimum temperature. In this way, we found that what is the desired coating concentration. For that, we have taken another statistical analysis, that is a factorial design. So where it will give you the interaction effect between the two parameters. So there are different parameters in statistical analysis. So you can choose one of those and can analyze your data statistically to interpret the results. So you have lots of data. But what is the meaning of those data? You need to do this by analyzing those data. And again, we found that what are the reproducibility. These two, if you are going for any sensor designing, or any, if a product designing also, so you need to find that what is the repeatability. Means basically it is used for sensor, that whether it is giving you the similar kind of result each and every day, or there is any degradation or anything happening. So you need to understand those things. And what are the reproducibility? You are preparing one sensor today, another day you are preparing another sensor, but those two sensor has the similar kind of result or not. So you need to check those things extensively, not just two sensor you are making and checking, not like that. You have to take lots of sensor, lots, because it's the probability you may have that two sensor are giving the similar kind of result, but maybe the third sensor is not giving the similar kind of result. So it is not that luckily you will get this result, not like that. You have to do the extensive extensive experiment for getting the results, and whether you are what you are claiming is actually it is right or wrong. So you need to understand those things. So repeatability we have found, then reproducibility we found, and whether this reproducibility and repeatability are within the error limit, those things, this kind of whole data analysis you need to do. And so in this way we did the selectivity analysis, means whether it can select the individual adulterants, means if ammonium sulfate is mixed, whether it can detect that it, yeah, it is an ammonium sulfate, it's not, or it can say that it is adulterant. So whether your instrument is able to detect a particular adulterant, or it can say that it is an adulterated milk. So you need to test that thing also. So for my instrument, or the developed we developed, so that is not able to give the individual adulterants, but it can detect the ionic adulterants, and it can show that it is an adulterated milk. Then what is the lifetime? That is also another main important thing of if you are designing your own sensor, because you need to go for means you don't want an instrument which will just every day you need to change the sensor. You won't purchase those things. So what are the lifetime of the sensor? So here in that particular sensor, it has 1,000 times of dipping, and we have to check that thing also. And another thing is that calibrating solution. So mainly it is an electrochemical sensor. So for an electrochemical sensor, you have to have that some calibrating solution, because whenever you have to compare with some standard solution, if you go for a pH meter or something, so you have to have some buffer solution or some calibrating solution. Here I have taken, there also have different solutions we made, but finally we found that that's NaCl plus distilled water, this is the composition. So we found that this is giving us particular phase angle, and which is converted to particular voltage. So this particular phase angle is similar kind of the pure milk, and we can take this calibrating solution as we can take this solution as the calibrating solution. So in this way, I am showing some parameters, but there may be lots of parameters whenever you will do for some sensor designing or some sensor characterization. Okay. So for this, you will have, so this part of the product design, we did the sensor design, sensor characterization, and then we completed the sensor data analysis. Okay, so anyone have any question? No? Is it understandable?
Yes, ma'am.
Okay, thank you. So our sensor is ready. So if your sensor is ready, and if you know the sensor is working properly and it is able to fulfill your purpose, then it's 80-90% done, because sensor is the main for this electronic products. So for after that, you need to do the signal conditioning circuit design. Basically, the signal conditioning circuit is to just convert the output of the sensor. Here in my case, it is the phase angle. So I have to convert that phase angle into the electrical voltage. Why do we need the voltage? Because we can calculate, we can make some decision according to that voltage. We can simply do some, if this voltage is greater than this one, we can keep one comparator. Then this, we can say that green LED will glow. And if it is low, then red LED will glow. In that way, a basic circuit, if we can do, then also it will have the electronic product. But we need more, that we have to show that whether this is adulterant or not, means, and then we need calibration process. And for particular this sensor, we need calibration process more importantly, because this is a diffusion based sensor. So for that, actually the characterization, sensor characterization was important, because that characterization, what we found in the parameter, what the parameters we have found, we have to taken care of all the parameters in the signal conditioning circuit as well as in the microprocessor programming, microcontroller programming. Okay. So now we are going to the signal conditioning circuit. So see, first what we have done, we need a transformer. You can change with just voltage, means voltage regulator circuit. It is easily available in, means readily available for giving the 12 volt. I particularly need 12 plus minus 12 volt because I have used a different operational amplifier. That is one of the IC which actually amplifies your signal. So for that I needed those plus minus 12 volt, and I generated it from the main power supply, that is the 230 volt power supply. But in the circuit part mainly, so you see this is the function generator, means what we need this, because we need this to generate that particular, what we have optimized, that 5.6 kilohertz, in which frequency it is giving the maximum difference in phase angle between the pure and adulterated mix. So that frequency you need to generate. So for that you have one function generator. Now you are generating one sine wave of that frequency. Okay. So one sine wave you are passing through your sensor. Here I am passing through sensor. Another frequency, another sine wave you are passing without modifying it. So now we are getting it, we are passing, giving it to a phase detector circuit. So this phase detector circuit you need to design. So you can design a different phase detector circuit, but here for that it's just a comparator circuit. So what is the main purpose of the circuit is that you can see the output of the phase detector. This is a XOR gate. I hope you all know the XOR gate. If you don't know, this is a digital circuit. Actually, this do you know XOR gate?
Yes,
XOR
ma'am.
gate. So can you explain what is XOR gate?
Exclusive OR will have the functionality of OR only. Only the thing is, um, in the logic, if both are high, at that time it will be 0 as well. That means
Mhm.
if the both inputs are different, only then it will be high, basically.
Exactly. So when both input are different, or maybe you can see that you can tell that when maybe it will here we have two inputs are coming, but it can be 3, 4 many inputs. So when you have the particular high position, that means one position one. So when there is a odd number of one, then the output will be high, true only. So these things we are passing through this. This is another IC, that is XOR gate, which is functionality of having XOR gate. So this, the first square wave. So first we are converting the sine wave into a square wave, because it in the square wave will see the XOR functionality in a good manner, means better way. So for that we are passing it to the, we are getting a square wave. And when the sensor is not dipped in any liquid media, maybe in calibrating solution or maybe in the milk, it is not dipped, just open sensor. So that time you see that this is the output of the comparator one, means output of the first input in the XOR gate. And when it is dipping, this is having an output of another square wave. So in these two square waves, you can see that whenever this is 0, means this is low and this is high, these are the opposite of opposite inputs are getting. So that time the output of the XOR gate is having the high. So this is basically the fully electronics part. So in that way we are finding that yes, the phase angle is detected. And now this square wave we are passing to the phase to voltage conversion. So for that what we have to do, we have seen that the maximum 90-degree phase shift it can occur. So this 90-degree phase shift we are converting to the 5 volt with the help of a filter circuit, RC filter circuit. So for that, we have converted to 5 volt. Whenever 90-degree phase shift is there, this is 5, and whenever 0, then it is 0 volt. Okay, so that thing we are giving to the microcontroller. And when we are and why we are restricting it 5 volt, because the microcontroller which I have used here, it works on 5 volt. And that's why I have given this calibration process of 90-degree phase shift, means 0 to 5 volt range. I could have used, because the microcontroller basically it is a Atmega 328, I could have used that 3.3 volt also. But for 3.3 volt, if you mapping that 0 to 90 degree in 0 to 3.3, and if you are mapping 0 to 90 degree in 0 to 5 volt, you will have more flexibility in 0 to 5 volt range. So that thing you need to understand, how will you increase the resist, means how will you increase the output voltage so that it can detect, means it can differentiate between different voltages. So this you need to understand by doing the electronic circuit design. And now came to the calibration and testing methodology. So after 5 volt, so this calibration and testing methodology, you see that here also different sensor parameters what we are optimized, that thing are using, because we are keeping at 42 degrees centigrade temperature. Then we are passing either 5.6 kilohertz. So you need to have one switch that it will ask the input, means from the customer, why you have the low fat milk, or you will have the high fat milk. So for that you have to switch between these two frequency. And then again, so you have some reference voltage. So that reference voltage is experimentally found, because we found that this kind of this phase shift is maximum occur between the calibration, means in the calibrating solution, that is the NaCl solution, and the pure milk. So this 0.25 volt, we have converted that phase shift into 0.25 volt. So this phase shift 0.25 volt is normally happen for the pure milk, and if it exceeds those things, so we are after calibrating, it is giving an reference voltage, and after this reference voltage, whenever we are dipping in an adulterated milk, so if that voltage exceeds that reference voltage, we are telling that adulterated milk, and if it is within that range, we will say that it is a pure milk. So all those things are done by coding in the microcontroller. So no need to think and worry about the programming part for the customer. So they have to just put whether you have the low fat milk or high fat milk. In that way, you need to just choose the frequency. And maximum cases for the cow milk, we found that it is a low fat milk. So no need to change the frequency selecting switch also. So because we need, our main aim is to make an instrument which should be user friendly. So user doesn't care what is the electronic circuit, what to do things. So they just press the button. They need the output. So for that, it will just ask that whether you need to do the calibration or testing. So user will give whatever they require, and it will show okay accordingly. Okay. So this, after that, signal conditioning circuit design. So then, so whatever the circuit we have designed, so it was first in breadboard, because in breadboard, I think you all know the breadboard, because it is for the designing, means electronic circuit design purpose, so that you can easily open the different components from the breadboard. But whenever you are sure or you are confirmed that yeah, your circuit is working properly, then you have to move to the PCB design. Why? Because in breadboard, you are inserting the components, but it may happen the breadboard is not working properly, or it may happen there is some loose connection, or similar kind of things may happen. So to remove those errors, to these errors, you have to move to the PCB design, and it will also give you a neat and clean process. So, and it is a rigid process. So you, if you fail down also, then it will not means 1-2 times it will not affect the components also. But yeah, so but in the breadboard, it can have that your components may get loose, or it can pop up from that breadboard like this. So the breadboard for this PCB design, I generally use the different softwares are there. I have used the Eagle software, And this is the first prototype, first PCB design for that. And one also, yeah, we have to do the, what I was telling earlier, that we need to check what are the power consumption of this whole circuit. So I found after the PCB design, because you can have in the breadboard design, you can find some here the connection problem or something. So after PCB design, we found that it is getting around 1 watt of power it is taking. And another thing is that what are the errors you need to calculate. So for electronic product design, if you are going to deep into this product design, so you need to calculate the percentage error due to this electronic circuit, because if there is a problem of these ICs, or let's say I am applying 500 hertz because my maximum frequency, operating frequency is 500 hertz, but it may happen that because of the function generator, it is not exactly not giving the 500 hertz, it is giving 600 hertz. So there may be a data, so that data is erroneous, and you will eventually you will have a output, that is the error output, and it will give the instrument, the overall instrument will not give you the exact result, that whether it is a pure milk or adulterated milk. So for that you need to check all the error, you need to check the error analysis for this, whether it is giving your the result which you are anticipating, that is giving or not. Just like here the frequency generator, you need to check. Then what are the duty cycle of the op amp? Here I have used some op amps. So what are the duty cycle of those op amps? So the different kind of, I'm not going into the deep into this error analysis, but you have to do this part because it is necessary to make your product more accurate. Okay. So these parts are done. Then signal conditions, you found that after sensor design, we'll have signal conditioning circuit. We need to analyze the error of this circuit. What can be the, I mean, you need to anticipate the error that it may happen in this IC. So what is, and how this error is affecting your result, that also you need to calculate. Then you need to do the PCB design and of course the mechanical design, because you are visual. For my case, I didn't do that mechanical design in any software, but now if for the, because now there are some different softwares are there. So for those you can visualize that you can do, already you are expertise in this, so you can do this in 3D simulation, so your product should be like this. And in that manner you can design your PCB also, because you may have that switch and all those things, it will come on the top of the product, or it will, some part of the circuit will come in that place, some part of the circuit will come another place. So for that you need to visualize that thing, you need to do the 3D simulation in the software, and then you will have to do the PCB design. Or maybe you can, if it is a simple circuit, you can keep one single PCB in the product, and then it will operate like that. So it's up to your choice. And okay, so after all those things, yeah, do you have any question? No. Okay. So our product process, sensor design is done, then signal conditioning is done, error analysis, PCB design, all those things are done. Now we'll move to the prototype development. So for prototype development, you can visualize that product, or you can make the 3D simulation. So I will show how it for my case. Yeah. So this one is the first prototype, that is the only for the adulteration detection. But my main aim was to make a product which will be detecting the adulterants as well as the composition, means the fat, SNF, protein. So I will come to that point. So this is the first prototype which is only detecting the adulterants in milk. Okay. So I can play this video.
Moupali, you are not audible.
Yeah, so okay. So this video is not audible.
Oh, yeah, there's no sound.
Oh, there is no sound. Okay. Oh, sorry. So actually, first I have taken the initial solution and I dipped it there and found the calibration, that what is the voltage there, and after that I kept that sensor in the milk, and it is asking that whether you want to test. So we just press the button, and it is waiting for 1 minute, because it was the diffusion time what we have set. So it is now showing the pure milk because we have taken the pure milk samples. And then again we are dipping the, and we are wiping the sensor with the tissue paper and by dipping it in the normal water. And after that we have taken, this is the another milk sample, that is the adulterated milk, and we have pressed 2 because it is showing taste of 2. And after that it is taking another 1 minute, it is showing please wait. And after that it is giving the, you can see this is adulterated milk because it exceeds the voltage. So this is the thing we developed first, and with that just a minute. Yeah, so with that prototype we could we could detect the different adulterants, and which are the most dangerous adulterants generally found in the milk of India. So these are the detergent, then ammonium sulfate neutralizer. So they have different purpose, just like the neutralizer to neutralize the milk, so to remove the developed acidity in the milk, so you can keep the milk for several days. And then ammonium sulfate is also another chemical that is for used for to increase the shelf life, so it won't be cut kind of thing, so it will be intact the milk. But these all are um, means harmful for the human being, harmful for health. And but the adulterants which we couldn't detect at 1% concentration, yeah, these the adulterants we have detected at 1% concentration, but at 1% concentration we couldn't detect these urea, sucrose, formalin, water. So that also we found what are the problem, because the adulterants we could detect, these are the these have the ionic bond, and these are the covalent bond adulterants. So our instrument couldn't detect those things. But yeah, maximum thing of adulterants it can detect. Now we have initially we checked this is the, and yeah, we also did the limit of detection, that is called the LOD, that what is the minimum quantity it can detect. So we have checked that limit of detection with the sheet scanner, that is an Indian product. They have claimed that it is it can detect these adulterants, these are the limits, and we have checked that we have we can detect lower than that limit. So we are happy, okay, this adulterant, this instrument is working. Then we yeah, so then we need for the fat detection, because this is only for adulterants. So for fat detection, we went through the similar kind of thing, that is another sensor design, and that is the another signal conditioning circuit. I am not going to, but just wanted to know that this fat detection sensor and the fat detecting prototype, that is a small handle prototype, these all were done. And these are the total results. And now finally the packaging. So in the packaging, so there will be two kind of sensor, because our aim is to make adulterants plus composition of the milk to check. So for that here you can see this A is the heater, means temperature controller. So for that we are keeping at 42 degrees centigrade temperature, because that is an optimum temperature. And this B part is the your signal conditioning circuit which we are keeping. So this is the temperature controller A, and this is B. And after that we have kept, this is a non very basic design of this prototype. So but the operation was successful, but design is not so that much great. So this is a stainless steel cylindrical container was keeping, and it has the lid steel lid, and what we have seen that it has one thermocouple for temperature sensing, because we need to have this milk in that temperature, and then two sensors are there. One is fat sensor, another one is adulteration detecting sensor. Thermocouple is used for milk temperature, and then we have one controller. Now see here, we have used the controller, we have purchased that controller, but you can design your own controller also. That is another kind of research. So each and every part has the scope of research, so you can do, and you need to think that what is your main aim, and you need to go accordingly. Okay, so we have purchased this controller commercially, and this has a PID control mechanism. So okay, so just to make sure that this temperature is 42 degrees centigrade. And this is the top view of this instrument. So we have one switch. Now you see that we are not keeping that switch inside the PCB board, because we need to operate that switch. So we have to design in that way. So it should be in that on the top for the selecting the frequency, for because low fat and high fat has different frequency. And another switch is for selecting the sensor. So this was the first prototype we made. So you see that prototype development, and we have, of course, we have tested. But so far what we have tested is the laboratory testing. Okay, so there is a huge difference between the laboratory and field testing. And so, and also, yeah, we need to do the characterization of this prototype. So what does it, yeah, we need to do the characterization as well as to need the validation of the product, that yeah, whether your product is comparable with another existing product, whether it can beat or whether it can compete with the existing product or not. For that you need the validation, and it is very, very important part of any product. If you maybe electronic, maybe mechanical, whatever, but you need to do the validation that whether it is competing with the existing product or not. So for this product, we did the validation. So first we checked with different. So I have tested it in the Bosch. So, but that was the initial testing. Then we tested in. So we tested in different states like Bangalore, means Karnataka, then Maharashtra, part of some area. So these were giving different means successful results, and now we are validating with a commercial instruments. So for this, we have taken one instrument, that is the Milko screen. What I researched when I was going through the literature, means the product review. So we found three instruments which is able to detect the adulterants as well as the composition. So one is not available in the market, but other two, one is the Milko screen. So that Milko screen was there in the NDRI, that is the National Dairy Research Institute, Kalyani, India. So we have compared our instrument with that Milko screen. Okay. So there are different cows, and we have different cow samples, means 74 in the morning, evening. So you will have an extensive experiments with that sample, and whether they are giving. And one more thing is that we knew that we didn't know the samples, because in the laboratory you generally what I did, I was adding the adulterants, and I know that yeah, the samples, I know what are the adulterants is there. So there may be a chance of manipulation. But in the testing part, you don't have any manipulation, because every sample is unknown to you. So for that, it needs the validation thing. So what we did, so here I am giving the example of 15 cow sample, means milk samples. So we are checking, validating with the output of the Milko screen and the output of the proposed instrument. We have named it milk tester. Okay. So these are the voltage reading, and accordingly, where PM means pure milk and ADM means the adulterated milk. So the notable results were that yeah, it detected successfully the adulterants. But one thing is that this, if you see that C13 and 14, these two samples, so it is detected as normal in the output of the Milko screen, but it is detected as adulterated milk. And then we go for the further research, and we ask them that what are the problem in these two samples because our instrument is detecting it is as adulterated milk. So then we found that it is a mastitis affected cow, and we found another research and another topic of product development. So the milkoscreen is not able to detect this mastitis affected cow milk samples, but our instrument could detect, because the mastitis affected cow milk sample has the more ionic concentration, and as it is the ionic concentration based instrument, so it was able to detect. So this is one of the findings we found, and after that we see that this milko screen could detect the urea and normal water, but our instrument couldn't detect, and we found that it is because of covalent bond, and our instrument can detect 25% of urea and water adulteration in milk, and we are doing research for that, how to reduce that quantity concentration of that adulterants so that it can detect. And one more finding is that you see the first sample, that is the sodium chloride adulterated milk. So the sodium chloride is generally used to increase the density. So if you are adding water in milk, so your density will be affected. So if we add NaCl to that milk, the normal table salt, if you add that thing, so it will increase the density, so you cannot understand with that the lactometer, all those things. So our instrument could detect it, the adulterated, but output of the milko screen was not. It was normal. So these three are the major we found, and we are happy that it can compete with the standard means the commercial milk analyzers. And yeah, further we have done the characterization. So characterization of the prototype is also important, because whatever we have tested earlier, that is a laboratory environment, laboratory based testing, but whenever we are going to this field, different samples, different, so you need the characterization, and main characterization is the sensitivity and the specificity of this prototype. So what are those? So I will explain these things. So sensitivity is the ratio of true positive to the total positive. So what are the true positive? That means pure milk sample is truly detected as pure milk, and false positive is that pure milk sample is detected as adulterated milk. So we need to find that what is the sensitivity of this by this formula. And the specificity is that the true negative. What is the true negative? That adulterated milk sample is detected as adulterated milk. That is the true negative. And false negative is that adulterated milk sample is detected as pure milk sample. So these things are, these two terms are important in the product design, this prototype design, and we found that how much percentage, and these data are based on the field testing data. So it was, but yeah, the data set was not that much larger, because it may be the maybe 300, 400 or 1000 data samples, but we need more data to comment on this sensitivity and specificity, but these are the initial data set which I am showing. And also we found what is the total power consumption of this. So we found that main power consumption is because of this heater. So that the heater has one coil, that is a nitro wire. So that is specifically the electrical product, you can say. Any heater, you can say that is the electrical product. But whenever you are adding a controller system, control mechanism, that is going to be an electronic product. So but we found for this validation time, we found that the milko screen, which they don't have any specific thing for the heating of the milk. Heating is mainly done for maintaining the homogeneity in the milk, but they don't have any specific sample and specific heating system. But we have used that heating system, but later we didn't use that heating system, because we found that if we see if we want to check the freshly collected milk samples, so we don't need to go for heating, because it is already homogeneous, and what we were testing in the laboratory, it was a packet milk, and you need to do this. You can make the homogeneity by stirring also. So you can see you can cut this part also, the temperature part, because as it is getting means it is consuming more power. It is total. It is giving you the 84 watts. So if you just remove those heating system, so the total circuit will have 1 watt power. And finally, we have done some comparative study with the another two milk analyzer, and what their specification and what is our specification. So in the power consumption, you see these are the 50, 20, and our case it is 84 watt. But if we just remove this heating systems, because they don't have any heating system, so it is 1 watt. So for freshly collected milk sample, there are the results are similar, so we don't need this. So this is minimum here. Then dimension, weight, these are the basic specification we found. Then whether they can detect SNF protein, they can detect, but we are having in progress. And then we found that 5 adulterants, means generally I focused on these 5 adulterants. So they can detect except the NaCl. I explained this earlier. So but our instrument can check the NaCl. And oh sorry, this is the CSIR series, is the sheet scanner, but they don't have that product in market. So they are claiming that they are able to detect the NaCl, and our instrument is also can detect the NaCl. Then water urea, we are not yet detecting those things. And then what are the sample test time? So these are the complete specification for any instrument. You can see that there are some data sheets, some manuals. So and there is a calibration how to operate. So I made one manual also. So these things. So finally, you can see the first this process is the ideation and research, and the second process, this total all those things, is the execution. And after that, you need to launch. So that is another fully other departments. So this is the ideation, research, then execution, and then launch. So these are basically the overview of this electronic product development process. Yeah. So this is my site. I have another. So not only milk adulteration detection. So there are different soil moisture measurement, and in my postdoctoral research, I have actually my area is flexible electronics, printable electronics. So different tags, RFID tags. So these things you can see in my website. Yeah. So any question?
I have one question.
Hello.
So if
Yes.
you are selling this for 5,000 and they're selling this for 5 lakhs, so
Yes. No, see, it's not 5,000. Actually, it's the only component cost. I didn't attach any labor cost, means manufacturing. So it will have more cost, but not in lakhs.
yeah, but I wanted to say like it should be profitable to be sustainable. So
Yeah, so that's why I have to sell it. It's not 5,000. I have just checked with my whatever the components and needed. So that overall cost, the component only, the PCB designing, fabrication, that thing I have just counted, but it won't be in 5,000. So it will add the manufacturing cost, then selling cost. So all those costs will be there, but it may have that it will be in 50, 60,000 like that. But I didn't, means that launching of these things is not yet done. So I cannot give you the exact cost, but yeah.
yes, ma'am.
Thank you, Moupali, for the nice lecture. I think that our students will be inspired.
That is the main thing for this
Yeah.
lecture. Okay.
Okay. Yeah.
So no other questions? So,
Is it possible for you to share with us the initial slides, like questions and details and all that you share?
initial slides, just
I don't know if you can share your project book also, it will be nice only, but then I'm not sure if you can do.
Initial slides means which one?
The overview of different steps
This
in
one?
electronics.
Yeah, I can. Yeah, do I need to send it to you?
Yeah.
Yeah, I can send it.
It was an interesting session. Thank you.
Mhm.
Ma'am, you can share in this meeting, maybe. The recording will
Yeah,
be shared as well.
recording. Yeah, that will be good actually. I will also have one copy.
So,
Yeah, sure.
Okay.
Okay, then, yeah.
Okay then. If there is no question, that we can stop this meeting now.
thank you so much, ma'am.
Yeah, thanks to you. Yeah, thank you, professors also.
Okay, bye.
Okay, bye for now.
And the best wishes.
Thank you, sir.
Okay.
Okay, bye for now.